Hello? Yes. Okay. Hello and welcome to the fifth Sunday special Chai and Why session. We are actually at TIFR, at the BARC TIFR Peletron LINAC facility. And this is, if you've been anywhere in Mumbai, in South Mumbai, you might have seen this big tall tower. I don't know if you can see it on the screen right now. You actually have to be quite far away to see the whole tower. But anyway, we are going to be taking you to a tour, a virtual tour, of course, of this facility. If you're joining us on Zoom, please put your comments in the chat. If you're joining us on YouTube, please put your comments in the chat. And to take us through this today, we have Vishwajit is a PhD student in the Department of Nuclear and Atomic Physics, and he works in the Peletron, and he's going to be telling us all about it today. So I am excited. Let's go. Let's get started.
Hello. Yeah. Okay. So we are in front. We are in front of the BRC TIFR Peletron LINAC facility. Now we will enter in the Peletron control room.
So first thing we're going to do is go to the control room.
Yeah.
Yay. Let's go.
Yeah.
Okay. Oh wow, this looks fantastic.
Yeah.
Oh wow, this is the place from which everything is controlled.
Yeah. Everything is control of the Peletron machines and LINAC machine. Okay.
So yeah. Okay. Let's see. So okay. So I guess we will come to the control system a little later.
Yeah.
But maybe we should start with what are we trying to do in this Peletron?
Exactly.
We're studying nuclear physics.
Yes,
right?
nuclear physics. So
and how do you do this?
Yeah. So before introducing all the machines, so I want to introduce.
Okay. Get into the background.
Yeah. So I want to introduce about some basic term. So all of you know about the discovery of the nucleus, right?
So there's the atom. The atom has all these electrons moving around, and the center there's a nucleus.
Yes.
Okay.
It's done by.
And audience, you can tell us what do you think the nucleus has inside it? Put it in the chat. What does the nucleus have mostly? What is the nucleus made up of? Let us know in the chat. Let's see what people are saying. What are they saying? Is the nucleus made up of? What's the nucleus made up of?
So the nucleus made of protons and neutrons. Okay.
Protons and neutrons.
Yeah.
Okay.
So basically, Rutherford is done the experiment, and he discovered the nucleus. So what he have done, he have taken a thin foil of gold, and he have taken the alpha particles, and it's allowed it to cross the thin foil. And he have seen very interesting result. Like most of the alpha particles just cross the thin foil, thin gold foil, and few of the alpha particle is just scattered. And one alpha particle out of 10,000 alpha particles, it's basically scattered back. So from this observation, he discovered the nucleus. Okay.
So basically what he found is that the atom takes a lot of space.
Yes.
Nucleus is very small.
Very small.
Most of these alpha particles going straight through the film.
Yeah.
Right?
Yeah.
Some of them were feeling the nucleus and getting bent a little bit.
Yeah.
And only 1 in 10,000 actually hit the nucleus and went backward.
Yes, backward.
Okay.
So that means
that was done more than 100 years ago, right?
Yeah.
Of course, he did not have something as fancy as this.
Yes.
So what do we have here?
So now, so at that time, so 5.5 mega electron volt alpha particle was there. Okay. So most of do you know what is the mega electron volt? So if you say, let's say, okay, I'll explain later. So now, so at that time, only alpha particle was the source of the high energetical charge particle. But now, if you want to see, if you want to go inside the nucleus, and if you want to see the properties of the nucleus and the others, the excitation thing, and if you want to investigate the excitation and the interaction of the protons and neutrons inside the nuclear matter, then you have to enter inside the nucleus, or you have to go as closer as possible to the nucleus. But this is not the easy job to do, because your nucleus is the positively charged particle, and let's say you are sending some alpha particle. So alpha particle is also the positively charged particle. So when they go closer and closer, and they repel and repel more and more. Okay, so this is not the easy job to do. So there are some Coulombic repulsion. So they experience a Coulomb barrier when they touch. Okay, now to overcome, we have to overcome that Coulomb barrier if we want to go inside the nucleus. So that's why we need a high energetical projectile, high energetical alpha particle, high energetical other particles. Okay, so to increase the energy of the projectile, we have this machine called Peletron and LINAC. Yeah.
So basically, you're saying that the problem is that the nucleus has an overall positive charge.
Yes.
If I come with something else which has a positive charge, it's likely to get repelled by.
Yes.
So the only way to do it is come with so much energy that you can go bang straight inside.
Exactly. Yeah.
And hence you need this big machine to give these particles, these ions enough energy.
Yeah.
And that's what the Peletron
yes,
does.
That's what the Peletron does.
So how do we accelerate these
ions? So for this, so I have to explain the schematic diagram initially. Let's come here. So can you focus here? So if your energy is not much, then your alpha particle is basically scattered from the nucleus. And if your energy is much, then alpha particle can combine with the nucleus and make a new element here. Okay, now how we create these fast moving particles or projectiles? So you can see this is the schematic diagram of the Peletrons and LINAC. So the initial idea is to make the ion source. Ion source means, let's say, so from ion source you first create the negative ion. I mean, you add an electron with the atom, then it makes it's an ion, and then basically we accelerate in horizontal section from ion source to this left side direction, and then it's bent by the injector magnet. So you know the magnetic field can't bend the charge particle.
So this is happening on top of the tower,
on
right?
the top of the tower at 40 meter.
At 40 meter height. But I thought you wanted a positively charged particle, no?
Yeah.
But you're starting with the
negatively charged
particle.
Yes.
There's a trick in this.
Yes. So we have to accelerate the charge particle in two different sections of the Peletron. So this is the tandem accelerator. I'll explain why is this. So now your charge particle bend toward the vertical direction, and it's enter to the accelerating section. Okay, it's in accelerated section. So now, so basically we use this pellet. Can you see this? Okay. So this pellets.
Oh, this is why it's called a pelletron.
Pelletrons, yes.
Because these are these pellets.
Yes.
Okay.
So we transfer the charge by using these metallic pellets, and so that it can go up to 14 million volt.
Okay. So the idea is, how does one give energy to a charged particle? You have to accelerate it.
Yeah.
And the way to accelerate a charged particle is to put it between some high voltage.
Yes. Okay. Yes.
So, and how do we generate a high voltage? Static electricity, just by rubbing things. Yes. That's how you generate a high voltage. But they do this by using a chain of these pellets. These pellets. Oops, sorry, wow, that's heavier than I thought. So these pellets are going up and transferring the charge in this tower.
Yes.
And this charge is being the voltage is 14 million volts.
Yes, up to 14 million volts.
14 million volts.
I mean, if you compare from our household voltage, it's about 70,000 times than our household voltage. But the only difference is our household is AC, and this is for this it's a DC.
So 14 million volts DC is somewhere. Where is that voltage? In the middle or
yes, in the middle. In the middle.
In the middle.
Yeah.
Because this is a brilliant idea that we will double this voltage.
Yeah.
By flipping the charge.
Yes, exactly.
Okay. Exactly. How do we do that?
So now, so your charge particle basically accelerate up to this is negatively charged ion, and then we put a steeper foil. It's very thin foil made of carbon, and while your charge particle is go through that carbon foil, then some electrons tip, and it's become positively charged ion. Okay, now you have positively charged ion, and again, so as this is the high voltage, the middle portion is high voltage, and this is ground. and then again that charge particle, positively charged particle, is basically repelled by those positive voltage, and again we can accelerate the charged particle.
So basically the trick is,
Yeah.
you start with a negatively charged particle,
Yes.
you attract it,
Yes.
14 million volts,
Yes.
then you remove that negative charge,
Yes.
it becomes a positive particle,
Yes.
and now that same 14
Yes.
million volts pushes it away.
Yes.
So by the time you come down, you got 28
Yes.
million volts of like the
not 28. See, if you're, let's say, in the stopper, so if you lose, let's say, 5 electrons, and let's say, for example, let's say if you have a plate, let's say this is positive and this is 0, and if you take an electron from this to this, then the electrons acquire energy E into V.
correct.
Okay.
Yes.
And now if your the charge is, let's say, 2 electron volt, 2 into E, then the energy gain is 2 eV. So inside, so by using this TIFR foil, we basically remove more electron. Let's say if you use carbon beam, then you remove 6 electrons.
So
let's say
all the 6 electrons of
yes,
carbon.
yes. Let's say I remove all the 6 electrons from the carbon, and then it becomes 6 plus carbon, and then the total energy basically gained by that is 6 times than
Okay,
your
even
14
better.
million
So
volt.
okay, but for one electron it would have been 14.
Yes.
And again another 14 because you're repelling it something.
Yes. Yes.
But the beauty is, because we can strip all the electrons, we can
Yes.
even make carbon 6 plus.
Yes.
You can get 6 multiplied by
Yes.
that thing.
Exactly.
Wow.
Yeah.
So that's how you, and you can strip like this oxygen. Or
Yes.
you can
Yes.
strip-
Oxygen. Yes. Whatever I want.
So
Let's
what
say,
are the kind of you know, projectiles that you use on top at this ion
Okay.
source? What do you start with, carbon beams, or what kind of beams are there in
so
the
this
Peletron?
depends on your experiment. Let's say if you want to make some nucleus, one nucleus, you are interested in that nucleus, so I have to choose the target and the projectile combination so that I can make that nucleus, that
Right.
our interested nucleus.
Yeah. But typically what do you use here?
So
Carbon,
so carbon, lithium,
okay.
protons and
Proton,
nitrogens,
nitrogen.
oxygens, magnesium, calcium,
Okay.
up to iodine.
Up to iodine.
Yeah.
So for calcium, for example, you can strip all the 20 electrons.
It depends.
Or
I mean,
depends.
it depends.
Okay.
Yeah.
But for oxygen, you can strip all.
Yeah.
Wow. Okay, that's interesting.
And now, so in this way, so your 14 megavolt, you can go up to, if you take carbon, then you can go up to 98 MeV, mega electron volt. Okay.
So you can generate a lot of energetic particles
Exactly.
using this accelerator.
Yes.
And then what happens? Where do the particles go?
Okay. So now it's particle. We have energetical particle, and now we do the actual nuclear physics experiment. So
Okay.
that particle is have the enough energy to break the Coulomb barrier, and it can, I mean, combined with the another nucleus, and it can make the compound nucleus. Okay. So now we can do the experiment. So the thing is, so now, so that energetical beam, so we got here, let's say up to 98 MeV of the carbon. If you take carbon, now if you again want to increase the energy, then we can use the booster. So booster is linear accelerator. So this is superconducting linear accelerator. So we'll show you one by one the instruments, the machine parts after some time, and then we'll go to the actual one of the experimental hall. Okay.
Okay, great. That's great. So basically,
Okay, guys. We have a
we have a question.
we have a question from YouTube.
Yeah.
So I'll just read it out.
Yeah.
Question from Anindita: how are all these electrons stripped?
So
So
basically,
the question is,
Yeah.
how are all these electrons stripped?
so basically you use a thin carbon foil. Okay. So when your highly energetical charge particle it's go through this foil, then it's basically the electrons is just knock out basically. The
Okay.
electron basically stiff, and your charge particle only nucleus can go.
So there's a carbon foil.
Yeah.
These very energetic ions go through this. When
Yes.
they go through it, they just lose their electrons over there, and
Yes.
only the nuclear part,
Yeah.
the charge.
Yeah.
Ion
Only
goes out.
nuclear, yeah.
Okay, that's how it happens. I hope
Okay.
that answers
Because
the question.
because your electrons is loosely bound,
The
so it's
electrons are
loosely bound. Yeah.
Okay. All right.
Yeah.
So now, are we going to see where this beam goes?
Yes.
Okay.
Okay.
Let's
Let's
go.
go.
Okay.
Yeah. So now we are going to one of the LINAC hall. So the LINAC is used as a booster of the charged particle. So if we need more energy, then we use the superconducting magnet. Okay. Sorry, not superconducting, not magnet. Sorry, superconducting accelerator.
Audience, we are now going to go inside a lab, and it's going to be noisy because there are pumps, there are lots of magnets and power supplies and everything else. So the suggestion is, please use headphones if you're listening, because there's going to be a lot of background noise, and that might be the best way for you to enjoy what's happening. Okay, so yeah, come.
Okay. So, okay, so take a view from here. Okay, come. You can come.
Wow, this is all impressive. Let's go. Let's go. Wow.
Okay.
So we are now at the bottom of the tower.
Yes, bottom of the tower.
This is where the beam comes in.
Yes.
And it sort of comes like this. One of the directions is this.
Yes, yes.
Okay,
So,
now you're going to tell us what happens over here.
So the beam basically bends from vertical to horizontal by using a bending magnet, and the beam come here. And now we have to keep the entire beam line in vacuum. Otherwise, your beam basically interact with the charge with the air molecules, and then we got lost the beam. Okay. Now, so this is the entire beam line. So this is the sublimator pump to maintain the vacuum of the beam line at 10 to the power minus 7 or 8 millibar.
So what is this? What is this?
So this is the quadruple. This is the quadruple magnet to focus. So during beam transport, so there is a chance to defocus the beam. So that's why we put the quadruple magnet to focus the charged particle. And now, so this is the dipole magnet, or you can say simply bending magnet. So here you can bend the charged particle. And now,
so just
yes.
So basically, there are two types of magnets.
Yeah.
There are magnets that make sure that the beam remains focused inside this tube.
Yes.
And there are magnets that make sure that the beam is bent correctly.
Yes. Yes. Okay. Exactly. Yes.
And these are either dipoles or quadrupoles or things like
this.
Right?
Yes.
Okay. So these are the magnets which are either focusing a beam,
yes,
or they are bending the beam where we want it to go.
Yes. Exactly.
Okay, wow, there are some big things out here.
Yes. So now this is the cryostat for the quarter wave resonator, where we increase the energy of the charged particle more. Okay. So you can see there are 3 cryostat. So inside this cryostat, we put the quarter wave resonator. So this bigger one, this one, and we have 3 here. Okay, you can go that side. Okay, so these 3 cryostat. So inside this, we put a lead coated with copper quarter wave resonator. So basically, what happened is that, so if you want to increase the energy of the charged particles, okay, so or if you want to generate, okay.
So can you tell us what's inside one of these things?
Yes.
Can we bring it?
Yes.
Let's
Yes.
bring it,
Yes.
let's bring
Yes.
it. Okay.
Let's bring it. After that, I think it should be easier to explain. Okay. So inside this cryostat, bigger cryostat, we have lead coated copper quarter wave resonator. Okay. So normally, if you have only copper tube, then you can generate on 1 megavolt field, 1 megavolt per meter field by using 1 megawatt power. Okay, so that's why we basically keep this thing in liquid helium. Okay, so that we can generate 1 megavolt field per meter by using only 6 watt or few watt.
So basically, because of the lead coating,
yes,
the lead is a superconductor.
Yes.
And instead of having only copper, now you are having a superconducting
yes,
cavity.
Yes.
And instead of using 1 megawatt power, you can use only 6 watts.
Yes.
Only 6
yes,
watts is enough to get that
few megawatt, few megavolt.
So this is what is inside those big cylinders that you were seeing there.
Yes. So so basically, this region is basically the gap. So where we can accelerate the charge particles.
So the charge particles are going through this.
Yes, through this
thing.
Through this thing. Yeah.
Okay. Awesome.
Okay. Now,
long shot.
Yes, take a long shot. Okay, now we put four.
By the way, how do you make all this liquid helium and all? Is there a liquid helium thing here?
Yes. So this is the liquid refrigerator for liquid helium, and this one bigger one. Okay, and these two are the DER for liquid nitrogens. So basically from here we basically distribute the liquid helium and nitrogen to each of the cryostat. Okay.
And I see some big balloons on top. What are those?
Okay. So basically, so during the power transport of the from the radio frequency, okay, so we have some evaporation of the liquid helium and it makes gas. Okay, so as the liquid helium is costly, so that's why we have to we have to collect the gas helium, and then we again process, we make it liquid helium, and then we again reuse that. So to store the helium gases, we keep the balloons.
Okay, so hopefully you don't have to use it, but in case there's a power failure and you lose the thing, instead of wasting the helium, you can wrap it in the balloons and then use it up again.
Yes, exactly. Yeah.
Okay, so here what you have done is that beam which came, it got sort of, the energy got boosted, and you bent it, and now it's going to go that way.
Yes. So we have again 4 cryostat to increase energy. Okay, you can come. Okay, here. These 4 are basically the cryostat for 4 cryostat again. So we have total 7 cryostat to increase the energy more. Okay. Okay.
And all these things can be controlled from the control room.
Yes, so all these things is controlled from the control room. Yeah.
Okay. So now where are we going?
So we are going to one of the experimental hall.
Okay, we'll go and see your experiment.
Yes.
Okay, great. Yeah.
So now we are going to one of our experimental hall where we actually perform nuclear physics experiment. Okay. So up to now we get the high energetical charge particles. Okay. Now we have to do the further focusing, and we have to use the slits to get the actual shape of the beam. I mean,
and then it will hit some target.
Then it will hit some nucleus, some target, and then we can make the compound nucleus. And after making compound nucleus, okay.
Oh wow. It says before entering the hall, ensure that the beam is off.
So
the beam is off, right?
Yes, the beam is off, because you can see there is an indicator. So if the beam is on, then you can see this. There is a red light.
Okay, so it's safe to go inside.
Yes, it's safe to go inside.
We are not going to get.
Yes, we're not going to get. Yeah.
Radiation from that. Okay, great.
Yeah.
Okay. Wow.
Okay. So this okay, you can explain.
Yeah. So this is some nice. Where is the experiment?
Zigzag thing. Yeah.
Oh, it's behind.
Yes,
okay,
behind.
okay,
Yeah.
it's behind.
You can come.
Oh, wow. Wow. Look at this wall.
Yeah.
Wow. What?
So
this is such a thick wall.
Yes, this is such a thick oil. It's about 1.2 meter thick oil. So during experiment, there is a chance to come up. If the radiation can come out from the experimental chamber, the gamma rays and some protons and some neutrons can come out. Okay, and then basically this thick wall is used to stop those radiation.
So even the idea is that so you first made a zigzag way, and there is this very thick concrete wall.
Yes.
So even if there is by mistake some radiation happening, there is that much of concrete.
Yes, exactly.
Even if the door was open or something, so there is no chance for any radiation outside.
Yeah.
Wow, 1.2 meters. Wow.
Yeah.
That's impressive.
Yeah. Okay, now.
Oh wow! Look at this.
Yeah. Yes, it's a good.
So these are all different experimental setups over here.
Yeah.
Okay. So these are all different experimental setups.
Yeah.
Okay.
So up to now we have got the high energetical charge particle. Okay. Now, up to now we get the high energy charge particles, or you can simply call projectiles, and basically this beam we have to focus again by using the quadruple magnet here, and then this. Okay, so then this beam is basically guided through these beam lines, and here we have a slit, X slit, to cut the diverge, some of the diverge beam, and here we have a bending magnet type is called dipole magnet, where we can bend the charge particle and we can send the charge particle to the respective experimental chamber.
So in a dipole magnet, there are just two coils, right?
Yes, there's two coils. You can. Yes.
So these are the two coils of the dipole magnet.
Yes.
And
So
this one, for example, has 4 coils.
yes, this is quadruple magnet. That's why it's a 4 coils.
This magnet has 4 coils. This is a
Yeah.
quadrupole magnet.
So yeah,
Okay.
so you generate NS repetitively, and then you base this module
For focusing the
yeah
beam.
for focusing the beam.
Okay.
Okay, and now this is the sublimator pump to maintain the vacuum at 10 to the power minus 7 millibar.
So the
Okay.
entire tube where
Yes.
the thing is at 10 to the minus 7
7
millibar
millibar.
pressure.
Yes,
Okay.
yes. So
They don't hit anything else by mistake.
yes, exactly.
Okay.
So now, and this is the slit. This is the slit. Okay, to focus the beam as well. I mean, to cut down the diverge beam charge particles. Okay, which is not in the focus line. Now, basically,
So here there is no experiment.
No.
This is just a beam line.
this
but
is also a beam line, and we can set up.
we can put an experiment here.
Yes.
Okay.
Yes.
So where is your experiment?
So my experiment is in that beam line. We can go there now. Okay. So at the end of each beam line, we have an experimental setup. Okay. So
This is also one experiment.
yeah, this is one
This is not
experimental
your
setup.
experiment.
No, this is not my experiment.
Okay. Well, what
Our
is this?
experimental setup. So this is the charge particle ball. So inside this, we put the charge particle detectors. Okay, and we put some fixed target nucleus, and when the high energetical projectile, I mean beam come, and then it's basically combined with the target nucleus, and then it makes the compound nucleus, and the compound nucleus is very unstable, and it's evaporates some protons and neutrons and some charge particles. Okay, lightly charged particle, and then we can detect those charge particle by using the charge particle detector inside this chamber. As your charge particle have the less penetration power, as the energy is few mega electron volt. So that's why all the charge particle we have to keep at vacuum inside this.
But
Okay.
this is not your experiment.
Yeah, this is not
Okay,
our
let's go to your
experiment. Okay. So okay. So this is the experimental setup. Okay.
Oh, wow. This is your experiment.
Yes, yes. So
So
here,
the beam is coming from there,
yes.
and
So there, and this is the array of gamma ray detectors and the charge particle detectors, basically. And we put, so there is a small chamber inside this bigger ball. Okay. So there is a, okay. So it's okay now. Okay. So there is a small chamber, aluminum chamber, inside this bigger ball. Okay, where we put the charge particles, and okay, and outside we put the gamma ray detectors in different angles. So what we do basically,
so these cylinders are all gamma ray detectors. These are all gamma ray
okay,
detectors.
not the cylinder, actually the composite form is basically the gamma ray detector, and these cylinders.
So is this experiment called the INGA experiment?
Yes. So this is the INGA setup. Its
So
full
what
name
is
is
INGA?
Indian National Gamma Array. I mean, this is
Indian
the
National Gamma,
Gamma
Array.
Array, the name of this setup.
So this is a very unique setup.
Yes, this is a very unique setup basically.
So how many such? So these are all gamma ray detectors
So
inside them.
yes, so we have total 19 detectors, 19 gamma ray detectors right now, but we can put up to 24 gamma ray detectors.
So you can surround this with 24 gamma ray detectors.
Yes.
And you can see how the gamma rays are going in different directions.
Yes,
That's
yes.
why you have detectors
Yes,
everywhere.
yes, exactly.
Okay.
So-
and what are all these tubes? What are all these
Okay,
white?
okay. So to reduce the noise, actually basically what happens is when the gamma ray basically interacts or gamma ray deposits some energy inside the detector crystal, then it creates some electron and hole pairs, and we are collecting those electrons by applying the high voltage. Okay, and corresponding to that we are getting a signals. But in room temperature, the noise is much. Okay, as you know, the PN Johnson basically gives the noise at dark current of the order of nanoampere. Okay, so then we have to reduce those noise. So how we reduce the noise? So we put the liquid nitrogen and we cool the crystal by using the liquid nitrogens. So the temperature of the liquid nitrogen is minus 196 degrees centigrade. Okay, so we cool our solid state detector, I mean the germanium detector up to that much. Okay, so for example, okay, anyway, okay, now I am talking about the gamma rays. So what do we do basically? So we put a fixed target and we use the high energetically beam, and then we produce first the compound nucleus, and that compound nucleus.
Maybe you can show what's inside this.
Yeah.
Yeah.
So here, can you come? Okay. So now inside this chamber, we put a fixed target, and we bombard the target by using the high energetic charge particles. Okay, and initially it makes the compound nucleus, and after that, as your compound nucleus is basically the very unstable, so within 10 to the power minus 19 or 10 to the minus 20 second, it evaporates some protons and some charge particles, or it can also break, and now the nucleus produce, but after evaporation, this is not going to the ground state. So it also in some excited state, so new nucleus will form here inside this chamber. And those new nucleus are in excited state. And from that excited state, it start decaying some gamma rays. Okay, some gamma rays in different direction, in different branching. Okay, so now we basically detect those gamma rays by using these gamma ray detectors, which is kept in different angles, so that we can do the study the some angular correlation kind of thing. Yeah.
So how expensive is one of these detectors?
So it's about 1 to 1.5 crores per detector.
So every detector is like
Yes.
1.5 crores.
Yes, 1.5
And you have
crores.
24 detectors.
Yes.
Wow.
It's so expensive detector because of, so it's not easy to, I mean, if you assume, let's say PN junction diode. So the impurity level in PN junction diode is 1:10 to the power 6. But for our case, the impurity level is 1:10 to the power 14. So this is high purity germanium detector, and this is very difficult to grow. So that's why it's basically the cost is so much. Okay.
So is this the detector?
Okay, this is the another gamma ray detector. This is also the single edge, I mean high purity germanium detector. This one.
So this is mainly just the shield for the liquid nitrogen.
Yes.
The crystal of germanium
Okay,
is inside this.
So crystal is here. Okay, after that there are some electronics, and there is a rod, copper rod, which touch the crystal, one of the crystal plane. And here we keep the liquid nitrogen, and there's from that liquid nitrogen is basically extract the heat from this crystal.
I see. Okay, yeah. So inside this is the germanium crystal.
Yes,
that
inside
is
this
going to be
germanium.
Okay. All right.
Okay.
There's something there.
So we have another detectors, the bigger gamma ray detector. So that is called Clover detector. So there we have 4 crystals together. Okay. So this is another gamma ray detectors. Okay, this is called Clover detector. This is also the high purity germanium detector. So here we have the crystals. We have 4 germanium crystal. So when your gamma ray basically deposits energy inside this, then electrons and hole pair generates, and we are collecting those electrons. And after that, we have some amplifiers to amplify the signals or the electrons. And then at the end, we'll get a signals. We get a voltage signals. At the end, we get a voltage signals from the detector, and now we process those signals, and we make it at the, I mean, we convert the analog signal to digital.
And this is all the electronics here?
Yes, this is all the electronics corresponding to this setup.
And you know which wire goes where?
Yes. Okay, so basically the signals directly coming from the detectors is basically go to some modules, and that module give you the digital number corresponding to the energy. Okay, and you can see here. So as I said, we have to keep the detector cool. So that's why we cool the detector at minus 196 degrees centigrade by liquid nitrogen. Okay, so now we are basically filling this detector door by the liquid nitrogens. Okay. Okay, now you can take a view of this. So this is basically the 4 pi gamma array. You can say this is a 4 pi gamma array. And yeah, if you have questions regarding this, then you put in chat box, then we'll answer you. Okay, and this is another detectors. Okay, come closer. This is another detector. This is the scintillator detector. This also used for detecting the gamma rays. Okay, so when a gamma ray energy basically deposits some energy inside this crystal, then instead of creating electron and hole pairs, it will create some scintillation light. Scintillation light means it have the wavelength of the order of 380 nanometer. Okay, and those electrons, those scintillation photon is basically focused to a photocathode, and then photoelectric effect can happen, and we get some electrons, and then we multiply those electrons. Okay. 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 Which one? Okay. No, no. Okay. So one of the beam lines you can see at the just in front of the walls. So this is in under construction. Yeah. So this beam line we use for some advanced projectiles, which is not easily available, and it's difficult to get. So for advanced experiment, we are basically constructing these beam lines. These are new beam lines. Okay, it is in under construction. Okay. Okay. It's enough.
You want to go back to the control room and explain what you do your physics, or you need something else over here? Have you explained your positron thing?
Yeah.
Okay. All right.
Okay.
Okay. So shall we go back to the control room now?
Yeah.
Okay.
Sure.
Go back to the control room.
Yeah. Okay. So yeah, can you see here? Yes. So
what are these?
okay. So these are the lead bricks basically. So when we so this is so heavy actually because of the high density.
Yeah, this is heavy. This is
really
heavy.
Okay, so we use the lead bricks to stop the gamma rays. I mean, to stop the radiation as well. I mean, sometimes we do some experiment using the radioactive sources, and from the radioactive sources, the gamma ray emits, and to stop those gamma rays, we use the lead bricks. Yeah.
Okay, so let's go back to the control room. Quieter, and you can tell us about some of the physics things that you're doing.
Yes.
Slow.
Yeah, okay.
Okay, that was really exciting. I mean, that is amazing to see this huge. To study the tiny particles, you need such a huge setup.
Yeah. So tiny particle means it's a really tiny. Like if you go to the nuclear dimension, for example, let's say if you take a small water drop. Okay, let's say this water drop is the size of the Earth. Okay, and how's your atom size? So this a small water drop is contain about 10 to the power 22 atoms.
Yep.
Okay.
Molecules.
Yeah, molecules you can say. Okay, and if you take a oxygen atom, then the size of the oxygen atoms is of the order of a motor seed. So whatever the nucleus, then if you take a very small dust, so that is the size of your nucleus. I mean, if you compare, like if your Earth is water drop, and then your motor is basically atoms, and a very small dust particle is your nucleus. So you understand how small.
Yeah, so the idea is if a water drop is like the size of the earth,
let's say size of the earth,
then an oxygen atom is like a small pea seed.
Yes.
And the nucleus will be like a small bit of dust.
Yes, very small. Yes, exactly.
And that's what you want to study. But to study that, you need all this kind of thing.
So inside that thing, so how is this thing? Is there any scale here?
So
is there any?
Okay. So, but what do you, your research?
Yeah.
What do you look at? You look at the shape of the nucleus.
Yes.
You look at it. What happens to it when this particle comes?
Yes, exactly. So in what we do basically using that INGA setup. So we basically excite the nucleus. So what is happening inside the nucleus? How is the shape of the nucleus? Okay. And so
the nucleus is not a sphere in shape?
Yeah, it's not sphere in shape actually. Okay, so we can see here. So nuclear can have different shape like spherical, it's prolate, it can have the oblate shape, it's octapole and hexadecapole, and the combination of some different shapes. For example, if you compare with the fruits, then you can see this is the orange and this is watermelon. It's let's say 186 polonium. Okay, it's a shape of the, let's say, your prolate shape, and then it's have the, I mean, if you compare with your fruits, then it's like watermelon. And let's say 186 mercury, then it's have the shape of tomato. It's if you remove this part. Okay, and yeah, and so on. And now your job is, can you say what is your known fruit?
So I mean, the nucleus is so small, right?
Yes, yes.
How do you know it is, like this pear shape, or it is like a little stretched or something?
So we basically excite the nucleus to very high spin state, and from that we can calculate the BE2 state. I mean, not B. Okay, you don't understand the BE2. Okay, so you basically measure the spin and the parity and the quadrupole moment and the lifetime of the state, and
so, what you measure. So you are doing this experiment where you are coming in with some beam, you are hitting your target, and in your INGA, that big system, you detect these radiations and charged particles going around in all directions. And from that data, you can figure out if the nucleus is spinning around,
or not,
how fast it is spinning, and also the shape. You calculate what the shape is. Because if the shape is different, the distribution of these particles will be different. Something like that. Okay.
So you can measure the quadrupole moment. After measuring the quadrupole moment, you can say about the shape.
So, and what is your own research about?
So I'm doing like some transfer reaction. Transfer reaction means like
so in your experiment, the experiment you do, what is your target? And what are you hitting?
Okay, so I am interested to produce 54 chromium nucleus. Okay, so for that,
so 54 chromium is chromium with
24 atomic protons.
24 protons, 30 neutrons.
Yes, 30 neutrons. Okay. So I want to generate that nucleus in excited state. Okay. Now for that, I am using the 50 titanium. 50 titanium means the mass number is 50 and atomic number is 22 with 7 lithium beam. Okay, so 7 lithium beam with, let's say, 20 mega electron volt energy. And so what happens? So we use the fixed target 50 titanium, and then it's bombarded and it's make the 57 manganese. I mean, 50 plus 7 is 57.
Right.
Okay, and it's
lithium
3
so
plus
22 becomes 25.
25. It's
so
manganese.
You end up getting 57 manganese.
Yes.
But you wanted chromium.
Yes, I want chromium. So now that is the compound nucleus, and that compound nucleus is unstable. So it evaporate. Let's say 1 protons and 2 neutrons.
So 1 proton goes away, 2 neutrons go away.
Then your nucleus becomes 54 chromium.
Okay, yeah, 57 minus 3 is 54.
Yes. Okay, 54 chromium, and that nucleus is basically in excited state. Okay, so there is any other channels also. It can evaporate 2 protons and some others way. Okay, but as I am interested to 54 chromium, so I am looking for only this. Okay, now.
So 54 chromium has some fixed energy. I mean, the nucleus also has some energy levels, like atoms have energy levels.
Yes. Like same thing.
You will look for some particular gamma ray which is going to come. You know that if I see this gamma ray, it means there is 54
54 chromium. Exactly.
Okay.
So then then that 54 chromium nucleus is basically emitting the gamma rays. Okay, and we are detecting those gamma rays by the gamma ray detector that I have shown there. Okay, okay, there's nothing actually here. Okay, so that I have shown. So then we detect the gamma ray energy, and at which angle with respect to beamline is coming, and in which path. So after emitting one gamma ray, in coincidence which gamma rays is emitting, and all those things we are doing analysis in our lab, and then we can predict something about the nucleus shape and the high spin, I mean the energy state of the nucleus, and we can say about the interaction of the neutrons proton with the nuclear matter and all those things. And another way is, let's say if you have low energy lithium beam, okay, so low energy lithium beam, I mean, then sometimes what happens, so let's say your nucleus is here, and if your projectiles, I mean, yeah, beam is come in this just head on direction, then it basically gives the compound nucleus. But if this is, it is not in the line, then what happened? So basically there is some interaction. Due to the interaction, the lithium can break into tritron and one helium. Helium mean alpha. One alpha and one triton, and the nucleus can capture those alpha particle to other scene, and it can make 54 chromium. So there's two ways to make. Like 7 lithium, we use the 7 lithium beam, so it's a cluster of one alpha particle plus tritron, 3 tritron. Tritron means it contains 1 proton and 2 neutrons. Helium, tritron, okay, like that. Okay, and so basically 7 lithium is a cluster of what I said, 7 tritron, 3 tritron, 1 tritron and 1 alpha particle, and the nucleus can capture that alpha particle, and then it can make 54 chromium
directly.
Yes, directly,
without going through manganese
yes,
and coming down.
Yes,
okay,
directly it can create. So, but there the states can different. The energy state, it's basically the populated at those energy state can be different. So we want to study, I mean, I am studying in that thing, like how the energy, is there any different of this energy state, and if how much the difference of the cross section via two process. Okay, so this is the all thing. Okay, so
and how long do these experiments take? So suppose today you start your experiment with
okay, so it's about
something
5 days day night experiment, 5 or 6 days day night experiment.
5 or 6 days, day and night.
Day and night, yes.
Day and night there are lithium atoms coming and hitting your
yes,
thing, and you will take data for 5 or 6 days, day and night.
Yes, exactly.
Okay, and all these experiments take a long time to do like this.
Yes,
right?
yes, because yeah, exactly.
And then you can do this only when there is a lithium beam. So when there's a carbon beam or something, then somebody else will come and do a different experiment.
Yeah, different experiment. So of course you can choose, because so we before experiment we basically do some simulation so that we can see if we choose this target and this projectile, then my interested nucleus can produce more. Okay, so along with the 54 chromium, others nucleus can also produce, and that nucleus behaves as a background. It's come as a background with my 54 chromium, right? So I want to reduce those others nucleus, and I want to make this experiment so that I can get the maximum 54 chromium, as I am interested to that nucleus.
Okay, great, great. So this lab runs 24/7.
Yes.
And it's all monitored from the control room here.
Yes. So from all this monitor, yeah.
So I think we have Avi. So do you want to tell us something about the control room?
Yes. Okay.
So wait, we'll just give him the mic so that we can hear him nicely.
Now you might have understood that everything is monitored through the control room, because all these experiments when are running, at that time there is a radiation which took place to safeguard human being from this radiation. Everything controlled from this control room. Okay. So we can see a different monitors.
So what in this control room? So there are lots and lots of, I see lots of screens, lots of electronics.
Yes.
So what is happening here? Yeah.
Here we will get control all these SF6 tank, various voltage, and these wall positions. manually we can control, remotely we can control all these walls from here. We can observe the various parameters and adjust depend on the requirement. This is LINAC control panel from where we can control all these quarter poles, magnets, and this momentum of all these beams. This is cryogenics control panel. In linear accelerator, we have to maintain all this cryostats temperature at liquid helium and liquid helium temperature, that is 4.2 Kelvin, or you can say this minus 200 is 69 degrees centigrade. The refrigerator, which we can maintain from here, same way we have to maintain vacuum and the level of liquid nitrogen and liquid helium in the cryostats. The secondary systems like this vacuum modules and this still water system is monitored and controlled by this panel. Same way we are having this vacuum panel here, from where all the vacuum modules we can observe the vacuum level of these cryostats and control the wall position.
Okay, great. So that was Ravi Deshpande, who is one of the operators out here on a Sunday. So 24/7 there is somebody in the control room, right?
Always.
Okay, good. And you know what's great? I'd like to introduce somebody else. So can we have Malik? Come on. So of course, at ChaiNY, we would like to encourage the students who are actually doing the research to be, showing us the labs, to be in the forefront. But we also have Professor Rudradoti Palit, who is the main PI on this INGA project and does a lot of the research at the Peletron facility here. So Palit, thank you so much for being here on a Sunday. I think maybe he didn't trust that we would be able to do it with this research. No. So Palit, is there something about the INGA array or something? This is not just a TIFR thing, right? This is a big national collaboration.
Yeah.
So why don't you tell us something about it?
Yeah. So see, the thing is, it's a Indian National Gamma Array which has started in 2001 with a lot of lot of people from different institutes coming together to put their resources. One good thing about INGA is people can do cutting edge experiments at the accelerators from universities and colleges, and they can propose experiments, they can do their test their ideas, and they can take the data and do the analysis. So that is one of the main feature of INGA, where high-end detectors can be used by people from all across the country, and sometimes people from outside India, they also come and do these experiments. So there is lot of possibilities for younger people.
This INGA, we were very lucky to see the INGA here today, but I believe the detectors also travel to different facilities in India, right?
Yeah. So there are 3 accelerator centers in India. Like one is at IUAC New Delhi, another is a cyclotron center in VCC Calcutta. So the detectors move between the 3 accelerator facilities, and many young students and researchers from IITs, universities, around 30 universities and universities, they participate in this experiment. So this is really a good opportunity for younger students for their PhD work. They work on this.
So this is a collaboration where 30 universities and other institutions have got
30
together.
universities, different research institutes, IITs, 5 IITs are also involved, and they propose experiments and do it. So,
and thanks to our experience with these gamma ray detectors, etc., I think we are also part of some international collaborative experiments as well, right?
Yeah. So because of our collaboration, our experience in this, and we have also a fantastic workshop in our TIFR. So because of this, we are part of the facility for anti-proton ion research in Germany, which is a next generation of radioactive ion beam experiment.
So look up FAIR. If you want to Google this, look up FAIR, the facility for anti-proton ion research. So and our group in TIFR is a part of this very large international project as well.
Yeah. So, and the other output of these experiments are like we can also develop detectors which can be used for medical applications. So Vishwajit, he has been working on, part of his work is development of those type of detectors and try to simulate and try to understand.
Great. Thanks so much, Palit. Thank you for being with us over here. Now, I am sure after looking at all this fantastic lab that you saw, you must have a lot of questions. So now is the time to ask Vishwajit questions. I'm just going to run and see if there are any questions on the chat or YouTube, and then sorry, Zoom or YouTube, and I will read them out, and then you can answer these questions. Okay? Sure. Are you all ready?
Yeah.
Okay, good. So let me just check out the questions, and let's see. Are there some interesting questions? Okay. Okay, great. So basically, but maybe we can answer some of those questions for the benefit of the audience as well. By the way, we've had two volunteers, Piku and Ananya, who have been on the Zoom chat all this while, or not Zoom, the YouTube chat, and they have been answering a lot of these questions. But so one of the questions was, you said there is a triton nucleus. So what is it?
Yes.
So what exactly is it? This is like,
so this
hydrogen is one proton.
Yeah, one
only.
proton. Now, if you add one neutron and one proton, and this is deuteron.
Deuteron, yeah,
Deuteron.
that's okay. And if you have one proton and
two
neutrons,
then
that's the nucleus of tritium.
Yes,
so that's what is called a triton.
Yes, triton. Yeah.
Triton is one proton and two neutrons.
Yeah.
Okay. The other question was, could you explain what is, you had some terms like prolate and these different shapes of the nucleus.
Yeah.
So there is a sphere is something which is like circular everywhere.
Yeah.
What is prolate?
So so there are two basically. So prolate means if you let's go there actually. So I think it's easier to explain. So basically, this is your spherical nucleus, okay, and prolate shape is like this. If you take a let's say egg, if you take an egg, then the shape of the egg is basically oblate shape, and if you take the 90-degree rotation of that, then you can get the prolate shape like this.
Okay. The other, there's one very interesting question.
Yeah.
Is that it seems that as you go to sort of bigger and bigger nuclei, the number of protons, like initially it's about the same.
Yeah.
Carbon has 6 and 6,
Mm.
but even when your chromium had, I think 24 and 30.
Yeah.
And when you go to some larger
Yeah,
nucleuses, it's the number of neutrons is much more.
Okay.
So why does the number of neutrons keep increasing as we go up in the periodic table of elements?
So that is because of it to compensate the nuclear. So if your nucleus is bigger, then basically the repulsion force between two protons will be bigger, right? So to compensate that repulsion, we need more neutrons
to keep it stable.
Yeah, to keep it stable. That's why.
Okay. But of course, the protons are held together by a different force. It's not just the electrostatic force. Right?
So the two protons are very close to each other, then it's experienced the nuclear short-range nuclear attractive force. And if the neutrons also, okay, so if they are so much close, and then it experiences short-range attractive force. Now, if your nucleus is bigger, then the protons which are apart far, okay, then your Coulombic repulsion force will come into the role. Okay, to compensate that, we have to put more neutrons to attract and bind together. Yeah.
Okay. And the other thing is, how do you sort of you said the nuclei were high spin states,
yes,
right?
Yes.
So somebody's asking, what are high spin states? I mean, the nucleus is actually spinning.
Yes, nucleus so is actually spinning with very high velocity, actually, you can say.
So this is really spinning. It's not like spin of an electron or something, which is just some concept. This is the nucleus is spinning.
It is spinning. Yes.
Okay, the nucleus is spinning.
Yes. So
okay,
your beam basically and your angle basically with high angular momentum. You can say more if you say from the quantum mechanical view, then you can say it have very high spin angular momentum. Yeah.
Okay. So are there any other questions on Zoom or YouTube? No. Okay, our volunteers are looking at it are saying no, which means I hope you.
I think Thanks to
So
Rakib
yeah,
and
we will thank Rakib also, who's been monitoring
Rakib,
our
Rakib, can you
chat.
come
You can
here?
just say hi, Rakib. Hi, thank you, Rakib, for helping us with controlling the computers for the live streaming. And on this note, then, thank you so much for coming to this virtual tour of our Peletron facility. We hope you like it. Maybe in future we will be able to have open days in TIFR where some of you might, if you're in Mumbai, come and get a chance to see these facilities yourself. Though, as you can see, today we were very lucky that there was no beam. Hence, we could actually go and visit these experiments. Obviously, when the system is running and there is a beam, then of course we can't go anywhere
there's no
nearby,
chance,
right?
yeah.
Okay. So on that note, let me remind you that Chai and Why happens first Sunday of the month at Prithvi Theatre in Juhu in Mumbai, third Sunday of the month at Ruparel College in Matunga. And if we have a fifth Sunday, then we will try to bring you live experiences from the lab like we did today, and we will keep you posted. So please follow us on Twitter. It's @ChaiandY, on Facebook @ChaiandY, or send an email to outreach, outreach @tifr.res.in. And on that note, have a safe weekend. Thank you for watching Chai and Why. Bye for now. And thank you. Thanks so much.
Thank you.
Yeah.
Okay. Okay.